Okay, so today we are going over some problems regarding splitting differences, more coin problems, and some basic logic. Um, so yeah, let's get straight into it. Um, okay, so our first problem, let's see. Alice buys a cookie for less than $1. She pays with two coins. One of the coins is a penny, the other is not. How much does the cookie cost? So if you remember from the warm-up problem, we need to recall that when we have problems such as these, we are looking for all possible answers, not just one. Um, so when we think about this problem, we have to consider all possible combinations of coins that this question permits. One of the coins is a penny, the other is not. The other condition is that the cookie has to be less than $1. So the sum of the 2 points has to be less than $1. Off the bat, you can realize that we do not have to mind the condition that the cookie is less than $1 because if we consider the largest possible value the cookie can be, considering that one of the coins is a penny, um, the largest possible cost of the cookie is 1 penny plus half a dollar, which is 51 cents, which is less than $1. Um, But yeah, when you're doing this problem, basically what we're going to do is add all possible combinations of the penny, the nickel, the penny and the dime, the penny and the quarter, and the penny and the half dollar. We can even do like a penny and a penny. Actually, no, because the other is not a penny. Okay, okay. Now that we've got this straight, let's look at the answer. So like as you can see here, we're adding up the different coins and the penny. So the cookie can cost 6 cents, 11 cents, 26 cents, and 51 cents. Okay, this problem is going to be quite similar to the last one. It's just going to be like backwards. So we're gonna see. Bob wants to buy a balloon that costs 12 cents. Bob has all sorts of coins in his piggy bank. Find all four different sets of coins Bob can use to pay for the balloon. Oh, just a sec. Okay. So, like the last problem, we are looking at combinations or sets of coins. However, in this problem, we're given the cost and we're asked to find the coins. Whereas the last one, we already were given sort of sets of coins and we were asked to find the cost. So it's like the last problem, but backwards. Um, okay, so off the bat, we know that, let me annotate. We know that the four sets of coins cannot contain a quarter and it cannot contain a half dollar. And the reason is because if the balloon costs 12 cents, um, and let's say we have a quarter, we can't there's no coin that can subtract cents from another coin. So therefore we can't have any coins that equal more than 12. Um, so a good way to start is by starting with the coins that are the smallest and have the least value, so the penny. One combination that we can come up with is 12 pennies. It's going to be my handwriting is very ugly, so 12 pennies can work, right? Um, if we consider the nickel, we can do something with, let me draw an arrow here. We can make a combination starting off with 1 nickel and uh 7 pennies, and we can even do 2 nickels and 2 pennies. We can move on to the next biggest coin, which is the dime. Let's say we have 1 dime. 1 dime is 10 cents. 12 cents minus 10 cents is 2 cents. So we can have 1 dime plus 2 pennies. And with these 4 solutions, we should be able to solve the problem, find all 4 different sets of coins. So yeah, let me clear the screen. So let's see the solution. Oh, okay, let me check. So first we got 12 pennies, 1 nickel and 7 pennies. Oh, the transition here is pretty cool. 2 nickels and 2 pennies, and 1 dime and 2 pennies. Okay, so the next couple of problems are going to be about splitting the difference. So what do I mean by this? Okay, let's start with an example problem. Alice and Bob have many coins. Alice has 2 more coins than Bob. How many coins should Alice give to Bob so that they both have the same number? So our first instinct might be, how can we find how many coins Alice needs to give to Bob if we don't even know how many coins they have? Well, with problems like these, when we're finding differences, the total amount that they each have doesn't actually matter. And the answer will be the same no matter how much is in these like bags of money. Like for example, like this could be 5, this could also be 5, and the answer would still turn out the same. So let's assign a placeholder number. Well, we're not going to be using the numbers. Let's assign a placeholder for the amount of coins that could be in this bag. Let's call it question mark because we don't know how much is in it. Okay. So that is question mark. And this one is also question mark. Draw an arrow there. We can assume that these question marks are the same. We don't know how much there is, but we know that there is the same in each of these bags. So we can say that question mark is equal to question mark. Alice has 2 more coins than Bob. We're given the difference and that those 2 points are here. In order to equalize the amount of coins they have, the way to do that is to take the difference between the 2 of them, divide the difference in half, and give 1/2 to the person with less, and let the other person keep the other half. The way that would work out, if we did it numerically, is Alice would have question mark plus 1 amount of coins, and Bob would also have question mark plus 1 amount of coins. Remember how I said that the question marks are equal to each other? If we add 1 to something that's equal to each other, then they're both equal to each other in the end. So we get this. And that proves that if we take the difference and we divide it in half, and give 1/2 to the person with less, they should have the same because question mark plus 1 is equal to question mark plus 1. Okay, let's move on to our next question. Also, if you have any questions, just leave them in the comments. I'll be looking at them and I can answer or send me an email, but whichever is easier would work. Okay, next question. So yeah, this is the solution. We got it right. It B. Okay. Next question. Charlie has 4 more pancakes than Donna. How many pancakes should Charlie give to Donna so they both have the same number? So let's visualize it. It's always a good idea to visualize the questions that you're doing, especially if they're more complex. They will help us understand the question better and will be hopefully helpful in solving it. Okay, so let's draw some pancakes, right? Charlie and Donna, they both have a stack of pancakes, and Charlie has 4 extra. So we're told by the problem that he has 4 extra pancakes, and Donna has a stack of pancakes We don't know how many pancakes are in the stacks. So again, let's assign a placeholder. Let's call this question mark. We can call it P for pancakes. Let's call it P. Um, again, we don't know how many pancakes they have, but again, like the last problem, it's not um very important to know how much P exactly is. And also like the last problem, these stacks are equal, right? P is equal to P. We're told that Charlie has 4 more pancakes. Like the last problem, what we're going to do is take the difference, which is 4, and we are going to take the difference and we can split it in half. When we split 4 in half, we get 2. We give one of the 2s to Donna, so we give 2 pancakes to Donna, and we leave the other 2 with Charlie. So this means uh, the answer is Charlie gives 2 pancakes to Donna to equalize. And we can prove this by saying, for example, P plus 2. So that's how much Charlie has because he has a set amount of number and 2 extra because there's 2 that's left. So P is equal to Donna's P plus the 2 that we gave her from Charlie's stack. Because the P's are the same, these 2 expressions on each side are equal, which proves that Charlie giving 2 to Donna will equalize the amount of pancakes they have. Okay, and let's check the solution. Yep, so we split the difference, so 4 divided by 2, or 4 into 2 parts. 2 equal parts is 2. We give 2 to Donna. Yes. Okay, okay. One last problem. I want you guys to realize that these problems all share a pattern, okay? So let's begin by reading the problem. Emily and Fabrizio collect stamps. Fabrizio has 100 more stamps than Emily. How many stamps should Fabrizio give to Emily so that they have the same number of stamps? Draw a picture, then solve the problem. Notice from the last 2 problems, they all follow a similar pattern in which they have they have the same type of item. So like there was coins in the first one, pancakes in the second, and stamps in this one. Um, but however, there is one person who has more than the other, and we're told how much more they have. In this problem, we are told Fabrizio has 100 more. In the last problem, Charlie had 4 more than Donna. And in the problem, even before that, Alice had 2 more than Bob. So we're given um, the difference between the 2. Again, since these problems are so similar, we should recognize that there's a pattern and that we should follow the same techniques that we used in the last one in order to solve this one. But first, we should follow the directions and draw a picture real quick. So let's get to that. Okay. Um, so as you can see, I did not draw this. I'm not Leonardo da Vinci, but here is a figure of 100 stamps. Note that it's actually quite easy to draw 100 stamps. If you draw a grid and then you draw 10 rows and 10 columns, since 10 times 10 is equal to 100. So yeah, um, like in the last couple of problems, the solution was to take the difference and divide it in half, give 1/2 to the person with less, and leave the remaining half with the other person. So we can do the same with this problem. Since we have 100 stamps drawn out here, we can divide it in half. So here I drew a line that divides it in half. If we count the number of stamps here, or if we use division, we get that there are 50 stamps in 1/2 of 100. So we give 50 stamps total to Emily, and Fabrizio can keep the other 50. So yeah, here's the solution. Fabrizio keeps 50 stamps and gives Emily the other 50 stamps. Um, okay, so this next problem is fairly interesting. In many math problems you'll get in the future, you're going to be given like a diagram or a picture. However, this problem shows us that sometimes we can't take the diagrams that we see at face value, and we have to fully internalize and understand what the diagram is showing us. So let's read the problem. Okay. All the chocolates in a square box were squares of the same size. Okay, so immediately when we look at this diagram, we see a bunch of squares that are of the same size. So it tells us these squares here, each of them individually could represent a chocolate. Okay, so there was one layer of chocolate in the box. That basically tells us like there isn't a stack of chocolate above this one, and that we don't have to worry about like being misled. Okay. Fleur and George ate all the chocolates from the box. George ate all the 12 chocolates along the rim. Use the grid on the right-hand side. Okay, so what this problem means by the rim is like something along the edge, right? So our first instinct here will actually pause for a bit and try to solve the problem yourself. Okay. And now I will go over the common misconception that this problem is going to teach us to avoid. Notice how George ate all 12 of the chocolates. The key phrase. This means that the entire rim only has 12 squares. When we look at this diagram, we might think that this this row here that this line is going through is the rim. However, this is probably not the case because if we count the number of squares in this edge, we get 1, 2, 3. I'm not going to write the numbers anymore. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 20 pieces of chocolate total if this box here were the rim of the chocolate. We are told that there are only 12 chocolates around the rim. So clearly, this here, like this area here, is not the chocolates that George ate. In fact, this rim here is not like there are no these are not chocolates. If we go another layer in, if we go another row in here, this rim, if we count the number of squares or chocolates there are, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This like ring of chocolates here are the chocolates that George ate. So we can assume that the bar of chocolates is not this entire picture, but is instead, let me highlight it in red. The actual bar of chocolates that's being depicted in this picture is this orange box here. Oh, that's not a good line. Okay. Let me redo that. It's this area here that's outlined by the red. Okay. So this is the picture of chocolates. Basically, what I want you guys to get out of this is when you're reading a problem, right? You need to understand what the question is one asking into how does the picture relate to the problem so that you can fully understand what the picture is trying to communicate with you. Now that we've figured out that the the chocolates that we are looking at that the problem is talking about is only contained within this red line, we can count to see how many Fleur ate. If George ate 12 chocolates all around the rim, it means that let me use blue for this. It means that the inner chocolates here are the ones that Fleur ate because all the chocolates were eaten in the end. And when we count the number of chocolates on the inside, the number of squares on the inside, we get 1, 2, 3, and 4. So the answer is that Fleur ate or pieces or squares of chocolate? And let's look over our answer. Or it for chocolates. See, it's these four that we were pointing at. So again, what I really want you guys to take away from this problem is to refer to the question when you're looking at diagrams. Don't take pictures and diagrams at face value. Otherwise, you can make the mistake of considering these as the squares that George ate and counting all 16 of these squares that as something that Fleur ate, when in fact Fleur only ate these four. George ate this. This here could be like a graph or a grid. It could even be the box itself, like the cardboard of the chocolate box. And of course, George wouldn't want to eat that. That's nobody should eat cardboard. Um, so yeah, check the diagrams with the questions so that we're actually understanding what the diagrams show. Okay, moving on to the next problem. These are going to be about logic and locks, or locks and logic. Okay, let's read the problem. There are two different keys that open two different locks. So one key will open one lock, the other key will open the other. So here's a picture here. The question asks, how many trials do you need to figure which key opens which lock? So a trial in this case means using a key on a lock. What are the outcomes of said trial? Normally when we're doing logic problems or problems that require logic, we need to consider all outcomes. So let's say that we let me get a pen. Okay. Let's say that we take this key and we try it on this lock. There are two outcomes, right? The outcome is that, first outcome is that the lock opens or the lock doesn't open. So what do either of these tell us? If the lock opens, we know that the key, that the blue key, let's call it the blue key opens lock one. Let me actually put some labels on them. So this is lock one. Oh, this is lock one. This is lock two. And this is the blue key. And we can call this ignore the color of the text. Oh, okay. We can call this, let's actually call it the orange key. Okay. Okay. Let's go back. So if the lock opens, we know that the blue key opens lock one. And from that, there's only there's only one remaining key and one remaining lock. And from that, you should know that okay, so let's say these two open each other. So we don't have to care about these anymore, right? If there's only one lock and one key left, we know that they must go together because they have to open each other. So from that one trial, we can figure out that this key opens this lock and this key opens that lock. But what if that lock doesn't open if we put the blue key into lock one? Well, we know that these keys in a certain combination will have to open both of these locks. This means that, if the blue key can't open lock one, it must be able to open lock two. So from that one trial, we can understand that blue key can open lock two. So since we know that these are a pair, we can ignore them. And then we're left with lock one and orange key. Since these are the only two left, we automatically know orange key opens lock one. So in both cases, after we do one trial, we can figure out from one trial which key can open which lock. So that leads us to our answer. Only one trial is necessary or needed. They mean the same thing. Or needed to know which key opens which lock. So that should be our answer. Okay, let's clear so that we can look at the solution. The answer is that I need one trial. Okay, great. Okay, this next problem is going to be similar, but it's going to be, I would say, considerably more complicated, but I think it's a good thing to go over. It's the same problem as last time, except there are 3 different keys that open 3 different locks. So here's our visual here. Consider the worst case scenario. How many trials do you need to figure which key opens which lock? So this question gives us a big hint with that like first sentence. Consider the worst case scenario. I think the worst case scenario would mean that we would have to use the most trials, right? So how many, like if the worst possible outcome happens, how many trials do we need in order to figure out, like if we're inconvenienced to the maximum, how many trials do we need to figure which key opens which lock? Okay. So let's go through let's go through the worst case scenario actually. Let's say actually let's first I'm gonna first label all of the locks. Okay, so this is lock 1. I'm gonna make that prettier. Here's lock 1, and I'm gonna change the color too so that we're not confused. Okay, here's lock 1. Here's lock 2. Here's lock 3. And for the keys, we can call this is the blue key. Oh, this is the red key. And this is the yellow key. Oh, you can't see that well. Okay, I'm gonna call this one the green key then. Okay, green key. Okay. So for our first trial, let's say that um we take the blue key here and we test it on the first lock. So consider what the 2 possible outcomes can be. The possible outcomes is that blue key opens lock 1, blue key doesn't open. Okay, so what are the ramifications or the effects if the blue key opens lock 1? Then we know that the red key and the green key can open lock 2 and 3. Let me extend this. And from our last problem, once we know a set can like open each other, it's good to sort of block them out because they're already known, right? So let's say we already know the blue key and 1 already open each other. We're left with the same problem as the problem we did before this, where we have 2 locks and 2 keys. From that problem, we know that if we're going to figure out like which key opens which lock, only one trial is needed. So from our text here, which this means that after that, only one more trial is needed to know which key opens which lock. And that would make a total of 2 trials. However, the question tells us to consider the worst possible scenario, right? So let's assume that blue key doesn't open lock 1. Um, so let's say that blue key doesn't open lock 1. What happens then? Um, so from that trial, the ramifications of that is that we know that the blue key can either open 2 or 3. So we can do one more trial then, right? Let's say that we do the trial again. The blue key can't open 2. That would mean that the blue key must open 3 because we processed of elimination out 1 and 2, right? So 2 trials with 1 key, the 1 key can't open anything. So we land with the blue key has to open the third lock because it must. So that's 2 trials gone already, right? Because there are 2 locks and 2 keys left, that means that we must do one more trial in order to determine which key can open which lock, which makes for a total of 3 trials. One trial to know blue key can't open 1. Second trial to know, let me extend this text box. Second trial to know blue key can't open 2. Can't open 2, which tells us blue key opens lock 3. And one more trial to know which block red and green opens. Let me pull that up. Oh, it cuts off. Okay. Okay. Yeah. So the answer, if we add them all up, it's 3 trials. Let me highlight it. 3 trials. That's going to be our final answer. Let me clear the page. You can pause if you want to read this explanation down here. Yes. So the answer is 3 trials are necessary. Okay, so that was the last problem of this problem set. Again, if you have any questions, please leave them down in the comments. I'll get to them as quickly as possible and I'll answer them as best as I can. I'll also upload a PDF on the website for homework problems that correspond to like the problems that showed up in this lecture. So I think it'd be very enriching to take a look at them and try solving them. And if you have any questions on those, again, leave them in the comments and see you next week. Thank you for tuning in. Have a good day.